If I would have looked at the spin-spin coupling constants, for example, which is the derivative with respect to nuclear magnetic moments, the story would have been different. Because then I wouldn't have this one, I just would have those three terms as the linear ones, and this one as the quadratic one. Indirect nuclear spin-spin coupling between two nuclei, which is the tensor. Let's look at, again, the alpha-beta component. That is, now let's just write proportional. Forget about all those natural constants right now. That's proportional to the second derivative of the energy in the presence of two nuclear magnetic moments. And then it's with respect to the alpha component of one and the beta component of the other one. So now I need all the terms which are linear. I guess I should put it this way around. I need all the terms which are linear in nuclear magnetic moments, those three, and I need the one which is bilinear in two different nuclear magnetic moments. So I get from the second order energy, from the second order Hamiltonian, I get this contribution with P, diamagnetic spin orbit, A, B, and now the alpha beta component of this operator, which is a tensor operator, which is just the second derivative of an energy having this as the second order Hamiltonian. And then I get a similar like this, plus sum of all excited states, E0 minus En. And then I get psi 0. And now I get all three of them in principle. As I in principle also had here in the shielding, in the second term for the shielding, I get all three of them. So I get P, PSO, A, and never mind which component, alpha component, plus P, A, SD, spin dipolar, the alpha component, plus P, A, alpha thermal contact, some Cn state. And at the same time I get, on the other hand side then I get Cn, and the same story again, but now the beta components, PSO plus spin dipolar, and that's nucleus B then, B beta plus P B beta of the thermal contact term, psi 0. And I guess I should have a factor of 2. Now, this one is just called the DSO, diamagnetic spin orbit contribution to the coupling constant. But let's look at this one now. If I take this first, that's a PSO that has no electronic spin operator in there. So it's not going to change the spin multiplicity of the wave function. So if we start with the closed shell, let's just think about closed shell molecules. So if I start with a singlet here, that has to be a singlet as well. So this is a singlet, and I start with a singlet. So the only one which goes in here is again the PSO term, PSO operator, because they don't change the spin. So I get a contribution then here, extra contribution, which is a sum over state contribution with twice the PSO operator. And that is called the PSO contribution, the paramagnetic spin orbit contribution to the coupling constant. So that's twice the PSO. So I've used the PSO, so I have the spin dipolar and the thermal contact, which are essentially the same operator. I mean, they are two parts of the same interaction, but they have the spin in there. So if I start with the singlet here, this is going to be a triplet state. So I could, I mean, this one is sort of sum over n, and so I have a singlet state, a PSO operator, alpha component, and again I have a singlet state here. singlet, PS, PSO, beta component, and the singlet, 0 minus the n. But here I'm going to have then sum over n. I start with a singlet. I have this spin dipolar plus p Fermi contact, alpha alpha, and therefore this is going to be a triplet state because of the spins. Then this is going to be a triplet, and I know I have to go back to the singlet, so again I can only use now an operator which has a spin in there. C0, which was a singlet. So I get one with those in here. And one normally actually splits them. That's in principle, you could write that as 4 terms. One with P is with the spin dipolar and a spin dipolar, and that's what you do. So you get a spin dipolar contribution, that's the 2 spin dipolar operators. You get a Fermi contact contribution where you have twice the Fermi contact term. And you get a cross term, what we call a cross term. Spin dipolar in one, Fermi contact in the other, plus Fermi contact in one and spin dipolar in the other, which is called the spin dipolar Fermi contact cross term. So you get actually 5 contributions if you really separate it out. But in a way you could treat those 3 together. So there are at least 3 contributions. There's the diamagnetic, because that's an ground state expectation value, and you have 2 sum over states expression, one where you sum over singlet states, and one where you sum over triplet states. And that actually, this term here makes spin-spin coupling constants more interesting than shieldings, at least when you're interested in electron correlation, because here you have to have a method which is able to describe excited triplet states properly. And whereas here you only have to describe excited singlet states, which is easier.